Welcome to Shining Creates Online School. Today I'll be taking you through Chemistry Paper 1, KALA Pre-Trial Examination 2026. Please, if you are new to this channel, find your time to subscribe to our YouTube channel, like our video, and as well comment your reactions at the end of this video. Welcome. Question number 1. Identify the Bunsen burner flame most suitable for eating in the laboratory. Give a reason for your answer. We need to understand that we have two main types of Bunsen burner flames. We have the non-luminous flame and the luminous flame. The non-luminous flame is the most suitable flame for eating in the laboratory, simply because it produces a lot of heat and it do not produce soot, something that is there in the luminous flame. So correct answer is non-luminous flame. So we have non-luminous flame. Reason: it do not produce soot, and we can also say it is very hot. It is very hot. You can say, or we can say it is the hottest. 1 mark for stating the flame and another mark for giving the reason. Part B of the question: incomplete combustion of laboratory gas may result in air pollution. Assuming that the laboratory gas is mainly butane, write an equation to illustrate this. We need to understand that butane burns in limited amount of oxygen to produce either carbon or carbon-2 oxide. But in most cases, carbon-2 oxide is produced accompanied by some production of water molecules. So the equation is butane, which is a gas at room temperature, reacts with oxygen, which is also a gas, to produce carbon-2 oxide, which is a gas, plus water molecule, which is a liquid. We balance with 2 on butane, we balance with 9 on oxygen, we balance with 8 on carbon-2 oxide, and we balance with 10 on water. And writing equation correctly with the correct set simples, and when balanced, it will award you 1 mark. Question 2, part A. Using dots and crosses to represent electrons, draw the structure of phosphyl chloride, POCl3. Given the relative atomic mass of phosphorus to be 15, oxygen 8, chlorine 17. Phosphorus reacts by gaining 3 electrons. Oxygen reacts by gaining 2 electrons, and chlorine reacts by gaining 1 electron. These atoms, they bond covalently by sharing their valence electrons. So we are going to have phosphorus at the middle, and then we shall have 3 chlorines, and then 1 oxygen. So we have 3 chlorines and 1 oxygen. Phosphorus reacts by gaining 3 electrons, and therefore we are going to fill chlorine, chlorine, will contribute 1 electron and gain 1. Chlorines contribute 1 electron and gain 1. And to show that chlorine or phosphorus has gained 3 electrons, which are the dots, for oxygen, I will use 2 crosses to show that phosphorus has gained the 3 dots, which are 3 electrons. Then on the chlorine's atoms, I will use dots to show that it gained the 1 cross, that is 1 electron. So I'll fill each chlorine with other 6 electrons. So I have in each chlorine, I'll fill it with 6 electrons, which are dots for chlorines. I'll still do the same on oxygen to show that oxygen gains 2 electrons, which are the crosses. And we shall notice that oxygen contributed its 2 valence electrons to bond with phosphorus. So the lone pairs of oxygen were natively bonded with phosphorus. So oxygen contributes all its 2 valence electrons to bond with phosphorus, and this is the correct uh, diagram for this compound phosphyl chloride, and this will only earn you 1 mark. Part B of this question: sulfur and oxygen belong to the same group of the periodic table. Explain why sulfur exists as a solid at room temperature while oxygen exists as a gas. We need to understand that sulfur is an octaatomic molecule, while oxygen is a diatomic molecule. And therefore, sulfur has stronger intermolecular forces than oxygen. And this gives sulfur higher melting point and boiling point. So we say sulfur, which is S8, is octaatomic, meaning it is made up of 8 atoms, while oxygen is diatomic, and hence sulfur has stronger intermolecular forces. That is the van der Waals forces of attraction than oxygen, and hence it has higher melting and boiling point than oxygen. And explaining this will give you 2 marks. Next question, number 3. Distinguish between empirical formula and molecular formula. Empirical formula, learners, empirical formula shows the simplest. Empirical formula shows the simplest whole number ratio in which atoms in which elements exist in a compound. While molecular formula shows the actual the molecular formula shows the actual number of atoms of each element in a compound. So each have a mark, and total mass is 1 mark. For instance, if I have glucose with C6H12O6, this is the molecular formula. When I simplify it to get the simplest whole number ratio, which is CH2O, this becomes the empirical formula. So this is the simplest whole number ratio, and we have the molecular formula, which shows the actual number of atoms. Next question, part B. When a certain mass of hydrocarbon was burnt in excess air, 0.54 grams of water and that 7.16 cubic centimeters of carbon dioxide were obtained at STP. Determine the empirical formula of a hydrocarbon given that carbon is 12 relative atomic mass, oxygen 16, hydrogen 1, and the molar gas volume is 22,400 cubic centimeters. So how do we determine the empirical formula of the unknown hydrocarbon? We are already given the amounts of carbon dioxide and the amounts of water produced. So how do we tackle this question? We begin by determining the respective masses of hydrogen and carbon from water and carbon dioxide respectively. So we can determine mass of, we begin by looking at the mass of hydrogen in water. How do we determine mass of hydrogen in water? We are already given the amount of water that was produced, 0.54 grams of water. And we already know the relative mass of hydrogen. We have 2 atoms of hydrogen. So we are going to have 2 over the relative mass of water, which is 2 plus 16, which is 18. And then we multiply by the total mass that was produced, total mass of water that was produced. And when you work it out, we are going to get 0.06 grams. That is the mass of hydrogen in water. Then how do we determine the mass of carbon dioxide in water? The mass of carbon dioxide in water, we are going first to determine the mass of carbon dioxide, and we want to work out the mass of carbon dioxide in water. We shall obtain, we are going to have, because we are given the molar gas volume, we shall take, looking at the mass of carbon, the molar gas volume, we are going to determine the mass. Because we are given the volume instead of the mass, we are going to take 44, which is the relative mass of carbon dioxide, multiplied by the volume that you are given, the volume of carbon dioxide, then we divide by 22,400. This is a shorter method that we can use, but if you want to do it the long way, we know the 22,400 cubic centimeters represents 1 mole. So you can first start by asking yourself, if 22,400 cubic centimeters is what about that 7.16 cubic centimeters? You get the number of moles. And then after getting the number of moles, you ask yourself, if 1 mole is equivalent to 44 grams, that's the relative molecular mass. What about what about the moles that you'll have obtained? And then you'll be able to get the mass of carbon dioxide that was produced. So when you do the calculation, you're going to get 0.073 grams. That is the mass of carbon dioxide. How do I get the mass of carbon in carbon dioxide? Mass of carbon in carbon dioxide, I'll take 12 over 44. I multiply by 12 is the relative atomic mass of carbon, 44 is the relative molecular mass of carbon dioxide. Then I multiply by the mass of carbon dioxide, and I'll be able to obtain 0.02 grams. And that is the mass of carbon in carbon dioxide. Then I use the method that we use to determine empirical formula. So I have carbon and I have hydrogen. Then the mass of carbon is 0.02 and the mass of hydrogen is 0.06. So we always start with the mass. After mass, we move to relative masses. So we have relative atomic masses. These are atoms. So we have 12 and we have 1. The mass of hydrogen is 1. So we work out the moles. Moles, we are going to take 0.02 divided by 12. When I take 0.02 divided by 12, I'll get 0.001667, and on the other side I will have 0.06. Then I divide by the smallest to get the ratio, the mole ratio. So I divide this by 0.001667 and I divide this by 0.001667. When I work it out to get the mole ratio, I'll get this is 1. And on the other side, I'll get 36.125. And it was noticed that this question had a typing error. And that's the reason we are obtaining something that is irrelevant. It is not something that has ever been obtained whenever we try to calculate the empirical formulas. So this question had a problem because if I was to round off, then we could have obtained CH36 as the empirical formula, and this cannot happen. So what you need to understand, you as a student, is just to take note of the method that I've used, and you shall be in a position to obtain the correct answer in future whenever you are given this kind of a question. So the method is very correct. The method is very correct, but the answer without it, because this is not this is not the answer that we could have obtained whenever we are looking for empirical formula. This does not exist. Therefore, it is unrealistic. But the method is very correct. There was a typing error in the question. Probably the volume of carbon dioxide that was given was wrong. Let's move to the next question. Ammonia gas is prepared in the laboratory using ammonium chloride as one of the reagents. Write a balanced chemical equation for the reaction. So we need to understand that ammonia gas is prepared by reacting ammonium chloride and calcium hydroxide. When they react, they produce calcium chloride and ammonia gas, and at the same time there is production of water molecules. So writing the equation, we have ammonium chloride, which is always a solid, and we react with calcium hydroxide, which is also a solid, and when they react, we obtain calcium chloride. Calcium chloride is again a solid, and we obtain our key product, which is ammonia gas, and at the same time we obtain water, which is a liquid. I balance the equation by putting a 2 on ammonia, and the equation becomes balanced. Part B of the question, explain how dry ammonia gas is collected in the laboratory. How do we collect dry ammonia gas in the laboratory? Once you prepare this gas, how do you collect it when dry? So what we do, we collect the gas using an upward delivery method after passing it through calcium oxide, which is the drying agent that is commonly used. So how do I collect a dry sample of this gas? So we say by use of upward delivery. So by use of upward delivery method, because it is less dense than air, because it is less dense than air, because it is less dense than air. You can also talk about after passing it through calcium oxide, which is the drying agent, and this is 1 mark. Explain how aqueous ammonia is prepared in the laboratory. So how do we prepare aqueous ammonia? It is bubbled in water through an inverted funnel. So we pass this gas through an inverted funnel. So we put water in a beaker, and then we use an inverted funnel and we pass the gas through it. We pass ammonia gas through that particular inverted funnel. So how do we prepare the aqueous ammonia? How do we prepare aqueous ammonia? So we say it is bubbled. It is bubbled in water. It is bubbled in water through an inverted funnel, which increases the surface area for the absorption or dissolution, for the dissolution of the gas, for the dissolution of the gas. And this gives you 1 mark. Question 5, part A, state the Gay-Lussac's law. This is used in the mole concept, and it tries to explain how gases react and how we use the knowledge of the mole to work out volumes of different gases. So we say, it states that when gases react, they do so in volumes that bear a simple ratio to one another and to that of the product if gaseous, and to that of the product if gaseous, and it is at constant temperature and pressure, constant conditions of temperature and pressure. And stating this will give you 1 mark. Moving to the next question, part B. 25 cubic centimeters of ethene gas is ignited in 60 cubic centimeters of oxygen gas at room temperature and pressure. Calculate the total volume of the gases at the end of the reaction. We can begin by writing the equation in which these gases react. So we have ethene gas reacting with oxygen to obtain carbon dioxide gas and water, which is a liquid. We balance the equation by putting a 3 on oxygen and putting 2 on carbon 4 and 2 on water. When you look at the mole ratios in which these gases react and how they are produced, we have 1 mole is to 3 moles is to 2 moles is to 2 moles. And we are being told that 25 cubic centimeters of ethene gas is ignited in 60 cubic centimeters of oxygen gas at room temperature. So when I look at whatever we are given, 60. So 60 cubic centimeters of oxygen were used. So I'll ask myself, for me to obtain the amount of ethene that was used, I'll ask myself if 3 moles oxygen needed 60 cubic centimeters. What about 1 for oxygen? So it needed how many for cubic centimeters for oxygen, which is 1 mole as per the mole ratio. So I'm going to have 1 times 60 divided by 3, and I'll get 20 cubic centimeters. So only 20 cubic centimeters were needed for ethene. And this also means if 1 mole is 20, then 2 moles should be 40 for carbon dioxide produced cubic centimeters, and also water. But what is not a gas? It could have been 40 if it was a gas. So we have 40 cubic centimeters of carbon dioxide. So we were given 25 cubic centimeters of ethene, and we have only used 20 cubic centimeters of ethene to react with 60 cubic centimeters of oxygen, and we are being told to calculate the total volume of the gases at the end. So the gas that we have at the end is carbon dioxide, which is 40 cubic centimeters, and we only used 20 from the 25 that we were given. So we can work out volume of ethene that remained. This amount is going to be 25 minus 20, and we are going to get 5 cubic centimeters. Then the amount of carbon dioxide that was produced is going to its 40 cubic centimeters. So total volume of the gas is going to be 40 plus 5, and the total volume of the gas is 45 cubic centimeters. 45 cubic centimeters, and these are working out these have a mark, working out these another have a mark, and getting correct answer 1 mark. Question number 6. In Kenya, Trona is obtained from Lake Magadi. Trona is a double salt with the formula NaCO3, NaHCO3 with 2 molecules of water. Write an equation to show the thermal decomposition of Trona. So when Trona is decomposed through heating, we produce sodium carbonate and carbon dioxide and a few molecules of water. So I write the thermal decomposition. I have a sodium carbonate, sodium hydrogen carbonate with 2 water molecules, and this is in form of a solution, so I can put a liquid or aqueous. Then I break this through heating, and I obtain sodium carbonate. And sodium carbonate in this case is a solid. I obtain water and I obtain carbon for oxide gas. I balance the equation by putting a 2 on Trona, by putting a 3 on sodium carbonate, and also by putting a 5 on water, and this gives you 1 whole mark. Part B of the question: describe how sodium carbonate is used in softening a sample of water that contains calcium chloride. So we have several methods of softening water, and one of them is by using sodium carbonate to soften water, add water. So how do we soften, add water using sodium carbonate? So we just add a solution of sodium carbonate. So we add sodium carbonate solution to the sample, add sodium carbonate solution to the sample water, to obtain calcium carbonate precipitate, filter out calcium carbonate precipitate, to obtain soft water as the filtrate. So this gives you 2 marks. Adding is going to give you 1 whole mark. Then filtering, I have a mark, and we have obtaining soft water, I have a mark. Question number 7. Then gas can be prepared in the laboratory by reacting a sort of carboxylic acid with soda lime. Write an equation for the reaction. We need to understand that alkanes, that is where it then comes from. Alkanes are prepared in the laboratory by reacting soda lime with appropriate sodium alkanoate. So how do we choose the most appropriate metal, sodium alkanoate? We choose the preceding metal alkanoate in that group of alkanes. For instance, if I want to prepare, then I shall use soda lime and sodium propanoate. If I was to prepare methane, I use soda lime and sodium ethanoate. If I was to prepare butane, then I use soda lime and sodium pentanoate. So I use the preceding alkanoate. So in my case, I'm going to prepare then by reacting sodium propanoate, and I react it with soda lime. So here I have sodium hydroxide, which is part of the soda lime because it's all a mixture of calcium oxide and sodium hydroxide. Then I react it with sodium propanoate. Sodium propanoate is a liquid. Not a liquid, but a solid. It's a solid form of a solid. And then in presence of calcium oxide, which makes it to be known as soda lime, and also some temperature, that is it, then ice produce sodium carbonate. Sodium carbonate is a solid, and I also obtain the key product, which is ethane gas. Equation is balanced, and this gives you 1 mark. Part B of the question: draw a setup of apparatus to show how the gas can be prepared and collected. So this gas, I'll use a flask. Then of course I'm going to support my flask using a stand. Then I want to collect this gas over water because the gas is lightly soluble in water. So I collect it using over water method. Then I can cork my flask, and then I place my mixture in my flask. So this is going a mixture of sodium propanoate and soda lime. It is a mixture of sodium propanoate and soda lime. Then there is it at this point. Then we have the delivery tube. Then my gas ethane is collected at this point over water. And then we have water at this point. So this is how the gas is collected. The marks are distributed on the reagents. Rating the reagents correctly, I have a mark. Using the appropriate method of gas collection, 1 mark. And workability on this case, is have a mark, and this gives you 2 marks. Moving to the next question: when 1 mole of ammonium chloride dissociates on heating, the enthalpy change for the reaction is positive 176 kilojoules. On the axis provided below, draw a labeled energy level diagram for the thermal dissociation of ammonium chloride. So the reaction, as we can see, is endothermic, meaning from the product reactants to products, it's increasing, so it's going to go up. So I'll begin by showing the reactants. So I have ammonium chloride. Ammonium chloride is solid, and then to form the products, I have ammonia gas, Then I also have ammonium chloride, which is also gas. We need to understand that the enthalpy change is at this point. So this is where the enthalpy change is, which is the change from the energy that had been used or had been absorbed to form the products. It is positive 176 kilojoules. Then we have this energy that has been used here, and this energy can make it dotted. The energy between that leads to the formation of the reactants or the products, we call it activation energy. This is the activation energy. So whenever the question is being marked, the marks are awarded writing correct reactant at the right position, showing the activation energy have a mark, showing the products have a mark, showing the enthalpy change have a mark. This totals to 2 marks. Part B of the question: calculate the enthalpy change that occurs when 10.7 grams of ammonium chloride dissociates completely, given that the relative atomic mass of nitrogen is 14, hydrogen is 11, chlorine at 5.5. We are supposed to work out the enthalpy change that occurs when 10.7 grams of ammonium chloride dissociates. So how do we work out this question? We determine the total moles of hydrogen chloride or ammonium chloride. So we are going to determine, we are already given the mass of ammonium chloride. So in this case, we can determine the moles of ammonium chloride in 10.7 grams of ammonium chloride. So relative formula mass of ammonium chloride, we have 14 plus 1 times 4 plus 35.5, and when you work out this correctly, we get 53.5, and this is mass, relative mass. To get the moles of ammonium chloride, we are going to have mass divided by the relative mass. So we have 10.7, we divide by the relative mass, which is 53.5, and when we work it out correctly, we shall get to 0.2 moles. So now we have the moles. We are being asked to calculate the enthalpy change. We already have the change or the enthalpy change that is equivalent to 1 mole, because we have been told that when 1 mole of ammonium chloride dissociates on heating, the enthalpy change for the reaction is 176 kilojoules. So it is in 1 mole. So we ask ourselves, if 1 mole of ammonium chloride is equivalent to 176 kilojoules, we ask ourselves, what about our 0.2 mole? When you work it out, 0.2 times 176, we divide by 1, we obtain 35.2 kilojoules. And in this case, not per mole, but just kilojoules. So this gives you 2 marks. Working out the moles, I have a mark. Working out the relative mass, I have a mark. And getting Correct answer 1 mark. So these totals to 2 marks. Question number 9. An acidic solution T was prepared by mixing 50 cubic centimeters of 1 molar hydrochloric acid with 50 cubic centimeters of 2 molar hydrochloric acid. Calculate the volume of gas produced at RTP relative, that is RTP when solution T reacts with excess zinc. Given that the molar gas volume is 24 liters. So we are looking at calculate the volume. So we have preparation of the acid. An acidic solution T was prepared by mixing 50 cubic centimeters of 1 molar hydrochloric with 50 of 2 molar hydrochloric acid. So we calculate the volume of the gas produced. So first, we are going to work out the moles in each solution. So the first acid solution before it was mixed up. So we work out the total moles. So we begin by looking at the total number of moles. Total number of moles of hydrochloric acid in the mixture. So we ask ourselves, we first look at the first set of hydrochloric acid, which is 1 molar 50 cubic centimeters. So we know capital M stands for 1 mole in 1,000 cubic centimeters, or 1 mole in 1 liter. So we ask ourselves, if 1 mole hydrochloric acid was in 1,000 cubic centimeters, what about 50 cubic centimeters? When we work it out, 50 times 1 divided by 1,000, we shall obtain 0 0.05 moles. And on the other case, for 2 molar, we ask ourselves, if 1 mole, 2 moles, because now we have 2 molar, so if 2 moles of HCl was in 1,000 cubic centimeters, what about 50 cubic centimeters? So when we work it out, 50 times 2 divided by 1,000, we obtain 0.10 moles. So to get the total moles of the acid, we take 0.10 plus 0.05 and we obtain 0.15 moles. 0.15 moles. Now that we have the moles of the acid that reacted, we can now standardize the zinc, or we determine the moles of zinc that were used. So we first now write the equation so that we determine the mole ratios. So zinc solid reacted with hydrochloric acid, which is aqueous, and we obtain zinc chloride, which is also aqueous. In this case, all chlorides are soluble, and we know lead and silver are the only chlorides that are not soluble, so it's aqueous. Plus, in this case, we always produce the gas, which is hydrogen gas. We balance the equation by putting a 2 on hydrochloric acid. And therefore, the mole ratio is 1:2:1:1. So, in this case, we already know the moles of the acid that were used, which is 0.15. We already know the moles, 0.15 0.15 moles. So how do I determine the moles of this? So automatically this is going to be 1 times 0.15 divided by 2. When I divide by 2, I obtain 0.075 moles. So these are the moles of zinc that were used. And the question says we determine the volume of the gas. We know this molar gas volume is always equal to 1 mole. So we ask ourselves if 1 mole of hydrogen is equivalent to 24 liters, what about 0.07 moles of the same gas? So it's going to be 0.07 times 24. We divide by 1, and when you work it out, we obtain 1.8 liters. 1.8 liters, and that gives you 1 mark. So it gives you 3 marks. Determining the moles of these half a mark. Determining the moles of the 2 molar acids have a mark. Writing the equation correctly, 1 mark. And getting correct answer, we obtain, that is determining the mole ratio, getting the moles of zinc have a mark, and getting correct answer have a mark. So this gives you total 3 marks. Moving to the next question. Question number 10. Propane reacts with 2 moles of hydrogen chloride gas to form an organic compound Z. Write the general formula of the homologous series that propane belong to. We know these are alkynes, and alkynes belong to a group of hydrocarbons with general formula CN H2N minus 2, meaning that if I have an alkyne with 2 carbons, then it will be C2, then H2 times 2, which is 4, minus 2, which is 2. And that is the reason ethine shall be 2 to C2H2. That is when N is equals to 2. You can find out when N is equals to 3, when N is equals to 4, when N is equals to 1,000, when N is equals to 50, and this formula will be in a position to help you obtain any alkyne in that particular homologous series. Draw and name the structure of compound Z. We are told that propane reacts with 2 moles of hydrogen chloride. So when 2 moles of hydrogen chloride react, let me just try to elaborate. I have ethine, propane, which is carbon triple bond, carbon. I balance here with hydrogen, and then I have hydrogen on this side. When I try to balance with 2 moles of hydrogen chloride, we expect the first step, we have HCl. It goes the first step, and then the bond breaks. Hydrogen breaks, comes to one of the carbons, and then we can obtain hydrogen C, then a double bond C, then C, hydrogen. So in this case, we are going to use the chlorine. So chlorine comes here. So it is now balanced when it's like that. this is addition reaction. So we have the hydrogen coming, chlorine coming at carbon 1, and hydrogen coming on the other carbon. When we move to the other mole, because this was the first mole, then we move to the other mole, the remaining 1 mole of hydrogen chloride, we shall break the remaining double bond, and one of the carbons, we already have chlorine coming there. One of the chlorine may come here, and then we are left, we have the hydrogen that was initially there. Then we have hydrogen, 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 and then we had the hydrogen there, and then we had the chlorine. We have the hydrogen that has also been discharged. It has also attached itself on the first carbon. That is one possible compound. Another possible compound is the carbon, instead of coming to the same carbon, the chlorine may come to the other carbon there, the second carbon. So that is again possible. So doing addition reaction, we have several possible compounds that could have been formed in that case. And the first one is the one that we have obtained, and we can have their structures. So let's look at their first structure. The first structure, we can have carbon, because we are going to moles. The first mole breaks the 2 bonds, and we have 3 bonds. One of them, we are left with 2. The other mole breaks the remaining 1 bond, and we are left with 1. Because we had 2, we are left with 1. So we can have C, C, C. Then we have hydrogen, hydrogen, hydrogen. Then we have hydrogen, hydrogen. And our 2 chlorines may have been attached. The 2 chlorines for the 2 moles may have been attached at the first carbon, on the first carbon, or this is a 1 dichloropropane, or we may have carbon, carbon, carbon. We may have the chlorines attaching on the second carbon, and then these are hydrogens. These are hydrogens, and the name becomes 2,2-dichloropropane. Or we may also have the chlorines attaching on different carbons. We have 1 chlorine attaching here and another chlorine attaching on the second carbon, and then these ones are filled with hydrogens. So this now becomes 1,2-dichloropropane. Dichloropropane. So these were possible answers that could have given. Give this one, you'll get a mark. If you give this one, you'll also get a mark. So any of these possible compounds were marked correct. So all of them were correct. Part C of the question. 3 drops of bromine water were added to compound Z. State the observations made. We know bromine water is one of the reagents that is used to determine the presence of double or triple bond in a compound or in an organic compound. When bromine water is added to anything with a double or a triple bond, it always decolorizes, or it changes to colorless. And because our compound Z does not have either of the two, does not have a double bond or a triple bond, we don't expect any significant change. So the yellow bromine water will remain yellow. So here we say yellow bromine water. Yellow bromine water remains yellow. Remains yellow. That gives you 1 mark. Next question. The setup below shows how nitrogen 1 oxide gas is prepared and collected in the laboratory. Study it and answer the questions that follow. We have a round bottomed flask, and inside it we have ammonium nitrate. We have ammonium nitrate. Then we have it. To speed up the reaction, then we have a delivery tube. Then we have the gas being collected being nitrogen 1 oxide and collected over water, meaning the gas is lightly soluble in water. Then we have a trap, and then we have water. It is preparation of nitrogen 1 oxide. Please take note of that. And we are preparing it by decomposing ammonium nitrate. Ammonium nitrate, the chemical symbol is ammonium nitrate. We have ammonium nitrate with a 3 O3. We are supposed now to describe how nitrogen 1 oxide gas is obtained in the round bottomed flask. So how is this gas obtained? This gas is obtained when we decompose ammonium nitrate by it. So ammonium nitrate, when heated, it undergoes thermal decomposition. To form nitrogen 1 oxide. Gas and steam. So that is how the gas is formed. Explaining this gives you 1 mark. Part B of the question. Write an equation for the reaction between nitrogen 1 oxide gas and heated copper tannings. Nitrogen 1 oxide gas, when reacted with copper tannings, the gas, this is one of the properties, the chemical properties of nitrogen 1 oxide. It's going to be reduced by copper. So itself is an oxidizing agent. So it's going to oxidize copper to copper oxide. So writing the equation, we have copper, which is a solid. We react it with nitrogen 1 oxide. Nitrogen 1 oxide is a gas. And when we react these two, we obtain copper oxide, which is a solid. The nitrogen 1 oxide is itself reduced to nitrogen gas, and we balance the equation. The equation is simply balanced. We have 1 copper, 2 nitrogens, 1 oxygen on both sides, and this gives you 1 mark for correct state simples. Next question. Pterilene is obtained by condensation polymerization. One of the monomers used in formation of pterilene is ethane 1,2-diol. Draw the structure of the other monomer used and give its UPAC name. To form or to prepare pterilene, pterilene is prepared by reacting ethane 1,2-diol. Ethane 1,2-diol, the formula of ethane 1,2-diol, we have HOC2 H 4OH. So we react it with another monomer which we call benzene 1,4-dioic acid. So we draw the structure of the other monomer, which is ethane 1,2-dioic acid, 1,4-dioic acid. So the ethane 1,2-dioic acid, that is benzene 1,4-dioic acid, the structure, there's always a benzene ring. We have a benzene ring. Then we have one carbon attached itself to an hydroxyl and an oxygen molecule, an oxygen atom, and the same repeats on the other side, one oxygen and one OH. And this is what we call benzene 1,4-dioic acid, ethane 1,4-dioic acid. And this is the formula and the UPAC name for this. Each have a mark. Part B of the question, state two uses of pterylene. Pterylene is a polymer and it has several uses. As we have in textile industry, it's used to make fabric, used to make fabric. It is also used in making conveyor belts, used in making conveyor belts. Also seat belts. It can also be used to make ropes, fishing nets. Can also be used to make plastic bottles, electric cables, wires, and insulators. So any two have a mark each, gives you one mark. Part B of the question, explain one disadvantage of continued use of pterylene. Pterylene is one of the non-biodegradable polymers and it can cause pollution. So we say it is non-biodegradable. It is non-biodegradable and it can cause pollution. We can also say when burned, it produces poisonous gases when inhaled. When burned, it produces poisonous gases when inhaled, and this may cause respiratory diseases. Any one mark. Question 13. The table below shows the colors observed when 3 drops of universal indicator were added separately to solutions W, X, and Y. Complete the table by filling the pH values of the solution. We know universal indicator, it's the indicator that is used and it's the position to show the strength of a substance, the strength of an acid, or the strength of a base. So we need to understand that when you use universal indicator, if it reads it shows the pH ranging between 0 to 3, it is always a strong acid and the color is always red. If it reads pH value ranging between 4 to 6, which is a weak acid, the color is either ranging between orange to green. If it's 7 or the pH 7, that is which is neutral, the color is always green for neutral. And a pH ranging between 8 to 10, which is a weak base, the color is always blue. And for 11, that's pH range between 11 to 14, which is a strong base, the color is always either purple or violet. So looking at what we are given, we are told to select a solution that can be used to illustrate acidic property of aluminium oxide. We have violet. Violet, of course, is violet. It is a strong base. Strong base. Red. Red. This is a strong acid. Strong acid. Yellow. Yellow is mostly, it is around, it is within the weak acid. This is a weak acid if it's yellow. So looking at what we are given here, select a solution that can be used to illustrate acidic property of aluminium oxide. Aluminium oxide is one of the amphoteric oxides. And first of all, we need to understand that aluminium oxide cannot even dissolve, so that it can be in a position to show its pH value, because it is insoluble. It's amphoteric oxide and it's insoluble. So we have, it could have been a weak acid if it dissolved, but now there's a problem with the solubility of aluminium oxide, because aluminium oxide is insoluble. But if we consider it, it could have been a strong base. It could have been a strong base, because aluminium is a more reactive metal. But we are going to leave this without no answer, because aluminium oxide do not dissolve, in water. So it cannot show its basic or acidic property, do not dissolve in water. So there's no way it can show its acidic property. But if you are to go for the answers that we are given, for the solution that we are given, it could have been a strong base, because aluminium oxide is one of the metals that is more reactive, and oxides of strong metals are strong bases. But for this, leave it that way. Part C of the question: state one advantage of using universal indicator over other commercial indicators. So I've said before that this indicator is in a position to show the strength of acids and bases. So it shows strength of acids and bases. It shows the strength of acids and bases. Question 14. Describe how a pure dry sample of lead 2 chloride can be prepared in the laboratory, starting with lead metal and dilute hydrochloric acid. So we are preparing an insoluble salt, lead 2 chloride. Lead 2 chloride is one of the chloride that is insoluble. So how do we prepare this insoluble salt? By starting with lead metal. So this is how we prepare this particular insoluble salt. So we add excess lead metal to a beaker. containing dilute nitric 5 acid. Remember, nitric 5 acid reacts with lead to form lead nitrate, which is soluble. To form containing dilute nitric 5 acid and star. Filter to remove excess lead metal. Add the filtrate to a beaker. Add the filtrate to a beaker containing dilute hydrochloric acid to precipitate out lead to chloride. Filter to obtain lead 2 chloride as residue. Then wash the residue with distilled water and dry between filter papers. So you have seen the process on how we prepare lead 2 chloride, which is insoluble salt. We first prepare a soluble salt of lead, and then we do precipitation reaction using lead 2 chloride. That is by reacting it with hydrochloric acid to obtain lead 2 chloride, where we then filter out and obtain lead 2 chloride residue. Then we wash and dry in between filter papers. This gives you 3 marks, explaining all the steps correctly. Question 15. The setup in the figure below was used to react carbon dioxide gas with heated charcoal. We know charcoal is just carbon. So carbon dioxide passes through a combustion tube that contains charcoal. And then we have aqueous sodium hydroxide. Placed within a boiling tube, and then we have gas X moving to another point. So what do we expect in the combustion tube? We expect carbon dioxide to be reduced to carbon 2 oxide, and the carbon 2 oxide is the gas X. Excess carbon dioxide is absorbed by aqueous sodium hydroxide at this point. So we write a balanced chemical equation for the reaction in the combustion tube. So what happens in the combustion tube? We have carbon dioxide gas reacting with carbon, which is a solid, and we obtain carbon 2 oxide gas. Balance the equation by balancing carbon 2 with a 2, and that equation gives you 1 mark. Part B of the question, state the role of aqueous sodium hydroxide in the setup above. The role of sodium hydroxide is to absorb excess or unreacted carbon dioxide. So this is to absorb unreacted carbon dioxide gas. Please learn to write in words so that you write the symbol correctly, because you may not be in a position to write the chemical symbol correctly. So when you're writing carbon dioxide, write in full carbon dioxide gas, and this gives you 1 mark. Part C of the question: two solid substances are produced when charcoal in the combustion tube is replaced with magnesium metal. Give the formula of each solid substance. So we need to understand that if I was reacting carbon 4 with magnesium, I could have obtained carbon and magnesium oxide. All these are solids. So the two solids that I could have obtained in this case shall be carbon and magnesium oxide. So give the formula. We are giving the formula of the two. So the first one is magnesium oxide and carbon. Each have a mark, that totals to 2 marks. That's 1 mark. Question 16. Sodium, magnesium, and aluminium are elements in period 3 of the periodic table with atomic numbers 11, 12, and 13 respectively. Explain the trend in ionic radius from sodium to aluminium. So we know if I was to write the electronic configurations of these metals, for sodium it's 281, magnesium is 282, and for aluminium is 283. As we move from right to left in the periodic table, in that particular period, there is increase in the number of protons across that period. An increase in the number of protons increases the nuclear charge, and this makes the atomic radius to decrease from right to left, or across the periodic, or from sodium to aluminium. So aluminium has small atomic radius than magnesium and also than sodium. So explaining the trade in ionic radius, we still use the same, and we say aluminium, the ionic radius decreases, and it is due to the increase in the number of protons, increasing the nuclear attraction. So we have been told to explain the trade in the ionic radius. So the ionic radius decreases. That is the first statement. Ionic radius decreases. So we explain by saying that this is due to increase in the number of protons from sodium to aluminium, which increases the nuclear attraction. The nuclear attraction. Therefore, the ionic radius from sodium to aluminium decreases. So this gives you half a mark, or that is 1 mark and 1 mark for explanation. Identify the element with the highest boiling point. Give a reason. Among the 3 elements that you are given, aluminium has the strongest metallic bond. So in my case, aluminium. So identifying aluminium, so have a mark, and then explaining the reason. It has the strongest metallic bonds. It has the strongest metallic bonds, and therefore higher melting and boiling point. So I have a mark again, and I have a mark on explanation. Question number 17. What the solubility of salts differs based on various factors. What is meant by the term solubility? What is meant by the term solubility? Solubility is the maximum amount of solute, is the maximum amount of solute that can saturate 100 grams of a solvent at a given temperature. At a given temperature. That is what we call solubility. So, the maximum amount of solute that can saturate 100 grams of a solvent at a given temperature. That's what we call solubility. Let's look at part B of the question. The mass of a solution of salt Z is 65 grams. The solution has 5 grams of salt Z dissolved in it. The solubility of this salt is 25 grams per 100 grams of water at 20 degrees Celsius. If 70 grams of the salt are added to the solution at 20 degrees Celsius, how much salt Z will remain undissolved? Let's look at this question. Let's break it down. We have mass of solution. Mass of solution is 65 grams. The mass of salt dissolved, is 5 grams. Mass of water, the mass of water shall be 65 minus 5, which is 60 grams. Solubility now at 20 degrees Celsius. Solubility at 20 degrees Celsius is 25 grams per 100 grams of water. That is the solubility. So we need to understand that we have additional salt added. Salt added. This is additional salt. Additional salt added is 70 grams. Remember, we had 5 grams that was already dissolved. So let's look at the maximum amount of salt that can dissolve in 60 grams of water. Maximum amount of salt that can dissolve in 60 grams of water, because we already have 60 grams, the water that we add. So we are given 70 more salt. So let's look at the maximum amount of salt that can dissolve in that 60 that we are given. We ask ourselves if 25 grams of salt can dissolve in 100 grams water. What about water being 60 grams? So it shall be 25 multiplied by 60 divided by 100, and when you work it out, we shall get 15. Only 15 grams are supposed to dissolve in 60 that we were given. But remember, we are given 70 and we had 5 that had already dissolved in water. So we only need 15 to dissolve in 60. So total salt added shall be the 70 that we had plus the initial 5, which is 75 grams of salt. We only needed 15. So the salt that should dissolve is 15. So the undissolved salt shall be 75 grams minus the 15 that was supposed to dissolve, and we shall have 60 grams of salt undissolved, and that is the correct answer. All that working shall give you 3 marks. That's how you work out the salt that was supposed, that remained undissolved. Remember, we had 70 and additional, and we had 5, and therefore our water can only hold 15 grams. So 60 grams of salt remained undissolved. Let's move to the next question. Name 2 crystalline alcohols of sulfur. We have 2 main crystalline alcohols of sulfur. We have the rhobic sulfur and the monoclinic sulfur. The rhobic sulfur, we also call it alpha sulfur, and the monoclinic sulfur, we also call it the beta sulfur. Alpha sulfur, rhobic sulfur is known as alpha sulfur because it is the common form of the allotropes of sulfur, which is stable at ordinary or normal conditions. So the 2 crystalline, we have rhobic, we have the rhobic sulfur, and we have monoclinic sulfur. Monoclinic sulfur. Each have a mark. Part B, write the electron arrangement of sulfur in sodium sulfate. We need to understand the rules that guide us on assigning the oxidation numbers. So we're looking at electron arrangement of sulfur in sodium sulfate. So in this case, I'm going to apply the rules that we use to award or to assign oxidation numbers. So here, I'm going to use the rule that says that the total number of oxidation, or the total number of oxidation numbers of atoms in a compound is equivalent to 0. I'm going to use that. So I'm going to have the one for sodium. So 2 into sodium plus sulfur plus 3 for oxygen, and this is supposed to give us 0. So the one that I'm looking for is for sulfur. The one for sodium, I know it's supposed to be positive 1 sodium, because I know sodium loses 1, plus the one for sulfur, plus 3 into 1 for oxygen, which is negative 2, is equals to 0. So it's going to be positive 2 plus sulfur plus negative 6 is equals to 0. So I want to be left with sulfur on this side. I have sulfur plus positive 2 minus 6. So positive 2 minus 6 is equals to 0. So sulfur is equals to positive 2 minus 0 is going to be negative 4. So when I take it on the other side, it's going to be positive 4. So this means that in this case, I know sulfur in the periodic table is number 16. So in this case, it means that sulfur lost 4. So if sulfur lost 4 electrons, then it shall be 12 in this case. So the configuration shall be 2, 8, 2. 2, 8, 2. Because when I lose 4 from this, I'll be left with 12 electrons. So the configuration is 2H2, and that gives me 1 mark. Next question. Write an ionic equation for the reaction between sodium sulfite and dilute hydrochloric acid. Sodium sulfite reacts with dilute hydrochloric acid to produce a gas which is sulfur 4 oxide gas. So in this case, I'm writing the ionic equation whereby I need sulfite ions, which are aqueous, plus the acid, which is hydrochloric acid, and I need 2 moles of the acid, and I obtain water, which is liquid, and sulfur 4 oxide gas. Why am I balancing with 2 for hydrogen? Because water has 2 atoms of hydrogen. So writing this correctly gives you 1 mark. Next, question number 19. A teacher of chemistry arranged the apparatus below in an experiment whose aim was to investigate the effect of an electric current on substances E, F, and G. Looking at the setups, we have set up E. The electrolyte that has been used is molten sulfur. F, we have molten or liquid mercury. And G, we have molten lead to bromide. In all cases, the electrodes are graphite solid. We explain the observations made in E. We start with E. You can see in E is sulfur. And the observation we are going to make on the bulb, we have a bulb at this point here. So we are looking at the observation made on the bulb. So the observation made on E is that the bulb does not light. Bulb does not light. This is because sulfur is non-electrolyte, or it is molecular. Sulfur is non-electrolyte, or we can say it is molecular. Then we have F. F, we have mercury, and as we know, mercury is a liquid metal at room temperature. And metals have the localized electrons. So here we say bulb lights. Bulb, mercury has the localized electrons. Mercury has the localized electrons. Mercury has the localized electrons. G, we have molten lead to bromide, and as we know, we have mobile ions in molten solutions. So in this case, the bulb lights. Bulb lights. The reason here is that molten lead to bromide contains mobile ions. Molten lead to bromide contains mobile ions responsible for electrical conductivity. Electrical conductivity. Giving or stating the observation, have a mark in each, and explaining, have a mark in each. And this gives you a total of 3 marks. Moving to the next question, question 20. Diazine is an unstable compound which reacts with oxygen gas according to the following equation. You can see the equation. Use the bond energies in the table below to calculate the enthalpy change for the reaction above. We already given the bonds of each and every reagent and the products and the bond energies of each. So how do you work out the enthalpy change? We are going to rewrite this equation by opening the compounds that we are given or the molecules that we are given. So in this case, to open diazine, I have H, N, then a double bond, N, H. That is how diazine bonds. For oxygen, we have 2 oxygen atoms, and we obtain nitrogen. Nitrogen has triple bond, and we obtain water. In this case, water, we open it this way, and we balance the equation. Water is balanced with 2, nitrogen is balanced with 2, diazine is balanced with 2. So looking at the bonds that we are given, we are going to do for the bond breaking. Bond breaking, it's always on the reagent side. For the bond breaking, we have hydrogen-nitrogen bond. Hydrogen-nitrogen bond is 388, and there are 2. So we shall have 388, there are 2, and we also have the 2 that balances that particular molecule. So we are going to have times 4 into 388. And then we move to oxygen. Oxygen is 496. Oxygen is 496. And before we go to oxygen, we also have nitrogen that is within the diazine, and it's times 2 in this case because we have the 2 that balances that molecule. So we are going to have 2 into 408, then plus the 1 for oxygen, which is 496 plus 496. 496. When we work it out, we shall obtain positive 2864. Positive 2864. That is for the bond breaking. Then we move to the bond formation on the product side. Bond formation. On the side of bond formation, we have 2 nitrogen atoms. So we shall have 2 into 944 plus, we have OH, 2 OH bonds for water. So we shall now multiply by 4. So it will be 4 because we already have the 2 that balances the water, and then the 2 for 2 hydrogen oxygen bonds. So we multiply by 4, and we use the 1 for OH bonds, so it's 463. When we work it out correctly, we shall get negative 3740. Why negative 3740? Why are we putting a negative? It's because bond breaking is an exothermic reaction, bond formation is an endothermic reaction. So for us now to get the enthalpy change is given by bond breaking plus bond formation. So in this case, I have positive 2864 plus minus 3740. When I work this out, I shall obtain negative 876 kilojoules. Negative 876 kilojoules per mole. So this, working out this 1 mark, working out this 1 mark, and getting the difference 1 mark. Moving to the next question, what is meant by Amphoterism? Amphoterism, learners, is the existence of compounds with both acidic and basic properties. Is the existence of compounds with both acidic and basic properties. This is 1 mark. For instance, we have the likes of examples of amphoteric substances. We have aluminium oxide, or aluminium hydroxide. We have lead oxide, 2 oxide. We also have zinc oxide. These are examples of amphoteric oxides. Part B of the question, when a few drops of aqueous ammonia are added to aqueous copper 2 nitrate, a pale blue precipitate is formed. The pale blue precipitate dissolves in excess ammonia to form a deep blue solution. Write a chemical equations for the reaction. So we understand that when I add a few drops, in this case, I already have a solution with copper 2 ions, which is aqueous, and I add a few drops of ammonia. A few drops of ammonia, I use the hydroxyl in ammonia, and I will obtain copper hydroxide, copper 2 hydroxide. Copper 2 hydroxide in this case is a solid, and it is the pale blue precipitate. Pale blue precipitate. Then I add it in excess. So in excess, so I add excess ammonia. Excess ammonia in this case, of course, I balance here with 2. Excess ammonia in this case, I'll use the precipitate, the copper 2 hydroxide, which is a solid. Then I add excess ammonia, which is a liquid. Excess ammonia dissolves the precipitate to form copper tetraamine ion. So we shall have copper with 4 ammonium molecules, and this is a complex ion with a positive 2. And then we add the OH here to balance the equation, and we balance it with a 2. So this is aqueous, and this is the deep blue solution. Deep blue solution. This tetraamine copper 2 ion, which is soluble, it is deep blue in color. It's not a precipitate, it's a solution which is deep blue in color. So those are the chemical equations that lead to formation of the deep blue solution. So writing this correctly, I have a 1 mark, and writing this correctly, 1 mark. Question 22. An organic compound Y can be obtained when propanol is added to crushed simsim seeds. Name the method used to obtain compound Y. So propanol we know is used as a solvent during the extraction of oils and other solvents. The method that we use to do this, we call it solvent extraction. This is the method of extracting substances from fruits, leaves, and other materials. We call it solvent extraction. Solvent extraction. Solvent extraction. Part B of the question. Describe how compound Y can be used in the laboratory to prepare a substance which improves the cleaning property of water. How can I use substance Y to prepare a substance which improves the cleaning property? We know substance, we are being told that an organic compound Y can be obtained when propanol is added to crushed simsim. So how do we use it to improve the cleaning property of water? So in this case, we are actually preparing water, not water but soap, because we have already extracted oil from simsim, and compound Y is oil. We have just obtained it from simsim seeds. So we are using it to prepare substance that can improve the cleaning property of water, and this substance is soap. So how do we prepare it? We heat a mixture of compound Y with either sodium hydroxide or potassium hydroxide. So we say heat a mixture of compound Y with sodium hydroxide, or you can also say potassium hydroxide, to boil. Then add sodium chloride, add sodium chloride crystals to precipitate out the soap. To precipitate out the soap. That's what we call sorting out. Then you can filter out the soap. Filter out to obtain soap. In this case, heating a mixture of compound Y with sodium hydroxide is 1 mark. Then adding sodium chloride, 1 mark, and doing the filtration, 1 mark. That's how we prepare soapy detergents. That's how we prepare soapy detergents in the laboratory. Question 23. Hydrogen gas can be prepared in the laboratory by reacting zinc granules with dilute hydrochloric acid. Name a suitable catalyst for the reaction. It is part of water and hydrogen that we prepare hydrogen gas in form 1. So the catalyst that is used during preparation of hydrogen gas is copper 2 sulfate crystals. So the suitable catalyst here is copper 2 sulfate crystals. So these act as a catalyst and it helps in production of more hydrogen at a very short time during the preparation of that particular gas. Part B of the question, describe how a dry sample of hydrogen gas can be collected. How can I collect a dry sample of hydrogen gas? I can pass the gas through either concentrated sulfuric 6 acid in a flask, or I can use a U-tube and I pack it with calcium oxide or calcium anhydrous calcium chloride as drying agents, and then I collect the gas using upward delivery. So we say pass the gas through concentrated, right in full, sulfuric 6 acid in a flask, or calcium oxide or anhydrous calcium chloride in a U-tube to dry the gas. Then collect the gas using upward delivery. And explaining this correctly gives you 2 marks. Next question, state Charles' law, this part of the gas laws. What does the Charles' law state? State that the volume of a fixed mass of the gas of a gas is directly proportional to its absolute temperature at constant pressure. So we say the volume is directly proportional to T. Means includes proportionality sign, then we shall have V over T is equals to K. So if I have two gases, then I shall have V1 over T1 is equals to V2 over T2. So the formula that we always use to determine calculations that involves Charles' law. So stating this correctly, 1 mark. Part B of the question, a balloon filled with air is likely to burst on a very hot sunny day. Explain in terms of the kinetic theory. How does this happen? So the reason is that there is increase in the kinetic energy of the particles, of the gaseous particles, and this increases the collisions, and when the collisions increases, the successful collisions increases, it leads to increase in pressure that makes the balloon to burst. So we say the kinetic energy of the gaseous particles of the gaseous particles increases increases, and this increases, and this increases the collisions. This increases the collisions within the walls, within the walls of the balloon, increasing the pressure. Increasing the pressure. And when pressure increases inside, then the balloon bursts. So explaining this correctly gives you 2 marks. Next question, question number 25. State is law. S law as applied in the energy changes. S law states that the energy change in converting reactants to products in a chemical reaction is the same regardless of the route, being followed, and this is at the same conditions. So that is what we call the S law. Part B of the question. Using the thermal data given in the table below, calculate the enthalpy change for the reaction. We can see that we have copper 2 sulfate solid and it's converted to copper 2 sulfate hydrated. So we have an hydrous form and hydrated form. Then we are given the processes. We have the copper solid. It can first change to copper, it can directly change to copper sulfate, aqueous, and we have the copper hydrated copper 2 sulfate that can change to aqueous copper 2 sulfate. So this is, if I have A plus B to obtain C, or I have A to obtain C, and I can still use A. I have B that I can convert A, I can convert to B, then I can convert B to C. So the energy change that I can use to convert A to B, that energy change, let's say my main aim is to obtain C. So I can first pass through B and then I obtain C. Then I can still use A to C directly and I obtain C directly like that. So if I was to obtain the energy change, let's say I was given this one as -2 and kilojoules per mole, and it is -3. So I'm being taught to obtain this energy change here. So I can obtain energy change at this point. So I need to understand that this energy change plus the energy change of converting B to C shall be equal to energy change of converting A to C directly. So this root is similar to this root. So if I was to call this one 1 and this 2 and this 3, then 1 plus 2 will be equal to 3. Or if I was to call this one small a, small b, and small c, then A plus B shall be equal to C. So I can be in a position to obtain the enthalpy change for the unknown side. So in our case, we are given the enthalpy changes. We are given the energy change. We are converting. Our main aim in this question is to convert copper sulfate solid to aqueous. So in this case, I can begin by having copper sulfate solid, and I can convert it to hydrated copper sulfate solid, and my main aim is to convert all of them to copper 2 sulfate aqueous. Copper sulfate aqueous. So I can pass through this route and I can pass through this route. When I look at whatever we are given, I'm already given the enthalpy change for converting solid to aqueous directly, and it is negative 156 kilojoules per mole. And I'm also given for hydrated to aqueous as positive 12.0 kilojoules per mole. So what we are not given is this enthalpy change. So we are told to calculate the enthalpy change for the reaction. So the enthalpy change shall be given by the enthalpy change. The enthalpy shall be given by the enthalpy of hydration copper sulfate, the enthalpy of hydration copper sulfate minus the enthalpy of hydration hydrated copper sulfate. The enthalpy of hydration hydrated copper sulfate. So in my case here, I shall have negative remember we have, if I was to call this 1 for this A, this B, then this C, I shall have used A plus B is equals to C. A plus B is equals to C. So I'm looking for the A. So if I'm looking for the A, I will have now C minus B. So in my case, we are going to have enthalpy of hydration copper sulfate, which is negative 156 kilojoules per mole, then minus positive 12.0 minus positive 12.0. So in this case, I shall obtain I will simply minus and I will get minus 168 kilojoules per mole. That becomes the correct answer. Next question, number 26. Carbon dioxide gas is classified as a greenhouse gas. Name 2 other greenhouse gases. We have several greenhouse gases that cause global warming. We can have nitrogen 1 oxide, can have ozone. We can also have methane. We can also have chlorofluorocarbons. And any 2 shall give you 1 mark. Part B of the question. Apart from the greenhouse effect, state one effect of accumulation of large amounts of carbon dioxide gas on the environment. So this one may lead to formation of acidic rain. So it leads to formation of acidic rain, which leads to death of aquatic and also terrestrial life. So this gives you 1 mark. Learners, this marks the end of our presentation today. If you found this video useful, please don't forget to like, comment, share, and most importantly, subscribe to our YouTube channel, Shiny Grades Online School, for you to be in a position to be notified whenever we drop a video of this type. Thank you very much for your support. May God bless you.